Hello, this is the first live session of this edition of the course called Behavioral Theory with a View Towards Data-Driven Control. My name is Debasattam. I'm your instructor. I'm here to interact with you live. If you have any questions, please go ahead and ask. I'll be happy to answer them. Questions वगैरह हैं पर हम्म, अच्छा। So far, we have not had any questions yet in this live session, which is understandable because only 1 week has passed so far since the starting of this edition of this course. So perhaps I can utilize this time to say some things about this course which might help you navigate through the course better. And also, maybe I can give some sort of ideas as to uh, what new discoveries are being made in this area. It turns out that this area of data-driven control has become very popular over the last few years, perhaps less than a decade even. What we do in this course is just, touching just scratching the surface of this entire, area of research, which is actively being worked upon these days. What we try to do in this course is we try to give the basics required to launch yourself into doing active research in data-driven control. So how data-driven control differs from the traditional approach in control is the key to understanding uh, what goes on in the area of what's going on in the area of data-driven control, and that is what we try to explain in this course. So as the name suggests, it really means that uh, from the traditional approach of control, where the first step always is to do modeling of your system. Whatever system you have at hand, you first do a first principle modeling. That can be based on the system's the physics involved in running the system. Yeah, so you look at the so-called approach of doing tearing and zooming, right? Have a system which might be a black box, might be a gray box, could be a white box. If it's a white box, then you know what elements are there inside the system. Like, for example, it could be, it could very well be it could very well be, it could very well be, sorry, an electrical circuit. Yeah, or it could be a robotic hand where you have what elements are there within the system. Like, for example, if it's a robotic hand, then there will be several motors and you can sort of tear and zoom. You can just look at one part of the robotic hand and say that, okay, this guy has, this DC motor, yeah, which is running this hinge, this part of the robotic hand. And then you write down the equations for this guy. There are different ways of writing down these equations. Yeah, you can use, this is just basic mechanics. You can either use Newton's laws or you can use other methods like, Lagrangian, yeah, all these, classical uh, mechanical, uh, you know, great, mm, great things about mathematical physics that you can employ here, and write down the equations for this system, right? That's the first principle modeling. If it's a gray box, then you just try to figure out how much information you have about the system, and based on that you try to do a first principle modeling. Of course, it will not match with the exact behavior of the system because some of the things are hidden. So those things you can treat them as uncertainties or you can treat them as noise. Yeah. And then there is the situation of a black box. And the traditional approach in control uh, literature or in control practice about such black boxes was always to identify the system. You look at the system, the black box, you give some chosen inputs, yeah, of your choice, some inputs that you like it could be a step input, it could be a ramp, it could be a pulse, it could be various pulses of various weights, yeah, or it could be sinusoids, yeah. So these are various different kinds of test inputs, test signals that you pass through the system and look at the output. And by looking at this input-output behavior, you try to get the system's equations. That is system identification. And then once the system identification is done, or the modeling has been done, you have the model at your disposal. Yeah, you have the equations at your disposal. Now, the moment you have equations at your disposal, you can bring in the entire might of control theory, yeah, to design a proper controller for the system, for the feedback control that achieves what you want the system to achieve. That's the traditional approach. What sort of control questions usually are asked? First of all, is it possible to do tracking of an input command? Is it possible to do regulation? Yeah, these are the two most basic control questions: tracking and regulation. Yeah, and tracking and regulation always has these ideas about whether while doing this tracking and regulation, one thing that you cannot discount at all is that the closed loop system you have to ensure is stable. So see, three control questions we have already seen: question of tracking, question of regulation, and question of stability, which also takes us to the idea of stabilization. Correct? And then related with these ideas, there are questions like disturbance rejection. Can you reject the disturbance? Can you design a controller which will make the effect of disturbance negligible, as small as possible? Yeah. Okay. Then later on, many other control questions were, sorry, were addressed. For example, is it possible to make a system passive? So a system which was not passive, is it possible to design a controller so the closed loop system will be passive? Passivation. That's what it became to be known. Yeah, so there are several control questions, and every control book is full of all full of various algorithms, various control techniques which achieve these control questions, these control tasks. And the traditional approach is that you have the system's equations. Somehow you have derived those equations either by doing basic first principle modeling or by doing some sort of system identification. Data-driven control, on the other hand, does the following. It says that, okay, I'm not going to do the system identification. Neither am I going to write down the system's equations from the first principle. What I will do instead. Oh, by the way, I missed a very important part about this regulation. Perhaps the most famous regulation control problem is the so-called linear quadratic regulator, LQR control. LQR control is so powerful. It's one of the optimal control techniques. It's so powerful that it is perhaps after PID control, that is the most prolific, most widely used control techniques ever. Right? So now, as I was saying that in data-driven control, you just don't care about this system identification at all. You don't care about the system's equations at all. What you do instead is you have input-output data, which could either be obtained via experiments or, listen carefully, they could also have been obtained from you know from running the system. Perhaps running the system is not in your hands at all. Somebody is running the system, and you're just collecting data about that system. Perhaps, say for example, let's say it's an economic system, a country's economy. You're looking at various variables, and their time series data is what you have. It could be the stock exchange data. Yeah, it could be um, some exoplanet in some exosolar system and the planet's motion data. Yeah, it could be a satellite's movement, that data. All sorts of data can be there. And you look at the data and you ask this question that from this data, is it possible for me to devise a control technique which will do the control for me without me having to first learn the equations? What is the benefit of that, you might ask? Well, the benefit, of course, one thing is that sometimes, writing down those equations, deriving those equations may be very difficult. Yeah, designing a controller might be an easier task. So why go through that lengthy and tedious and difficult process of obtaining the system's equations, right? Secondly, it may be so that, your the system identification may be impossible. There could be situations like, insufficient data. You may not be able to figure out the system uniquely. It might be an ill-posed problem. Is it possible to still design a controller which, at least given this data, would it be would it be possible to design a controller so that all those non-unique systems that you had, which could possibly have given rise to this data, all of them would be controlled, would be, if you use this control, it would be so that all those systems which are possible candidates for the so-called ground truth, that is the system that is generating this data, it will be able to achieve the control objectives for all those systems, all those candidate ground truth systems. Okay, and there are several uh, such good properties that can be stated about such this new data-driven approach. Of course, you can understand this idea of data-driven approach is is actually inspired by uh, the recent boom that we see in data-driven approach in every engineering field. Yeah, because our computation power has increased so much, these manifolds, that is why it now makes sense to collect enormous amount of data and then make your controller or devise a system, um, a computer, an artificial brain, which looks at this data and decides upon its controller, decide upon the solution for this control problem from the data on its own. Yeah. But the interesting bit here is that unlike unlike a usual machine learning, artificial intelligence, AI kind of an approach, where you treat the data as if, um, as if as if it's just raw data. You don't incorporate physics, ideas from physics, like where this data is coming from. Is this time series data coming from a DC motor, coming from a robotic hand, of whose, we have prior information about its equations? Then we should use that idea, you should use that theory in addition to what we have seen about, in addition to what a deep neural net can do. And that is where this idea of data-driven control comes in. So data-driven control, we don't talk about deep neural networks at all. We just look at this rudimentary problem of, having data from a system. We know that it is coming from a dynamical system, which has, we know that it's going to be linear differential equations. And from there, we try to understand, this control questions, whether they can be answered using, using this information and the data. It is our belief, it is our strong belief. So data-driven control research is going in two directions as of now. There is this idea of reinforcement learning-based control, which treats the data as it is, passes it through deep neural nets, and asks questions like, can we achieve optimal control of the system by doing reinforcement learning, by looking at, looking into these patterns in the system, and providing various inputs and keeping those inputs which are beneficial for the system, and discarding all those inputs which are not so. Yeah, that approach. And the other approach is that we don't use the language of deep neural nets at all. We just look at the data of the system, and from that data, we assume that this data is being generated by a system which is governed by linear differential equations. Yeah, and then decide upon the control from our ideas about controlling systems which are governed by differential equations. Right. So I hope I was able to give you some idea about what this course is about. Although we don't get to this idea of data-driven control much in this course, only at the very end we discuss a couple of problems from data-driven control. because we devote most of the time in this course in 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 giving you the foundation, giving you the 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 basic details, yeah, that lead us finally to this to that take us to a position where we can ask these questions of control, of data driven control, meaningfully. So we start with what is known as the behavioral approach in dynamical systems. So we define dynamical systems, we define the behavior of a dynamical system, which is nothing but the collection of all possible solutions of a given differential equation. And then we do this calculus of equations. We see how different set of equations can be derived from a given set of equations. What is the basic thread that connects all these different representations of the same system? What is unique from the system's point of view? The equations certainly are not unique, but if they are not, then what it is, what object it is that is unique in a given behavior, in a given system, given set of trajectories. Okay. Then once we discuss this idea of calculus of equations, we once we have calculus of equations, we also look at questions like basic systems theory questions like controllability, yeah, stabilizability, observability, yeah, and then we take a leap to this idea of going from time series to these equations. Yeah, if we have time series data from the behavior, of course, the entire behavior cannot be specified, right? That's like usually it will contain infinitely many trajectories, infinitely many solutions, out of which suppose only a finitely many solutions are given, and that too for a finite time duration. What do we do in that case? If we have such finite time series data of a system, then in that case, is it possible for us to determine the system's equations? Can we do identification? We answer that question. In that process, we learn this immensely important idea of persistently exciting signals. We see that such identifications are possible from a finite time series data if our input signal is persistently exciting. And the idea of persistently exciting inputs is rather non-trivial, because just having input which is there all along is not enough. It has to be such that it excites all possible modes of the system. If the system, we know from our theory of ordinary linear differential equations, this ordinary differential equation doesn't have to be linear. Even for non-linear differential equations, it's true that there are these ideas about the system's order. Yeah, the degree of freedom that the system has. That is the so-called state space dimension. Yeah, that dimension plays a role here. If you have an input which excites all these possible modes of that system, which is finitely many, of course, if it's an ordinary differential equation, then the input must be such that it excites all those modes. That is roughly what the meaning of persistently exciting input is. We make this precise in this course. If you go through the videos, you'll see we do discuss it at length. We actually give a proof of persistently exciting. This idea of this theory that persistently exciting input would imply that it is possible to identify the system. And then making that assumption, we solve this problem of, I think, stability problem we solve. I think controllability question also we answer. Yeah, and that is where we stop. We did not get the time to, this is a short course, so we did not get the time to discuss other issues. So I hope that you'll enjoy the videos very much. And I think we'll have one more opportunity to have such a live session in the coming few weeks, right? I would also encourage you to post questions offline, which can be answered. Okay, I think we can call it we can end the session now. All right. Enjoy the lectures. ठीक है ना? ठीक। Okay, thank you.